Let's go. Hope you guys like learning about thermal recovery. Third one in a row. My name's Britton Jackson.
Rihanna Reimars.
Mohammed Onizi.
And I'm Jake Roswell. And we're covering thermal enhanced oil recovery. So first off, why would we want to use thermal enhanced oil recovery? And as has been stated in the last two presentations, heating up your oil decreases its viscosity. And just like changing oil on your car, when you heat it up, your oil is going to drain faster than if you just tried to change your oil when it's cold. So adding this heat to the reservoir will decrease your mobility ratio and therefore increase your recovery factors, increase your production. And so the actual EOR methods we're covering, these are almost all of them. There's probably more I don't know about, but we're just covering those three right there. And that is cyclic steam injection, steam flooding or steam drive, and fire flooding or in situ combustion. So first of these is cyclic steam injection, which consists of injecting steam down your wellbore for a predetermined amount of time, usually maybe a few days or a full week, and then you allow that steam to sit there for 1 to 2 weeks, and the heat transfers from the steam into your reservoir and into the oil and lowers the viscosity of that oil. And the neat thing about this one is that you're using the same well for both injecting and producing. So there's no separate production well from the injection well. It's the exact same well that you're injecting into and producing from. And this is often called the huff and puff method, and you can continue to inject, wait, produce, and repeat that until it's uneconomic. So now steam flooding or steam drive is where you actually have a dedicated injection well, and then you would have one production well or multiple production wells that you're producing from. And steam is constantly injected down the wellbore and into the formation with this one. And just like before, the heat is transferred into the oil, decreasing its viscosity, lowering your mobility ratio, and pushing the oil towards your production wells. And the water will actually, the steam will condense into water, and it'll push just like water drive as it gets closer to that production well. And the last one we covered was fire flooding or in situ combustion, which is where you actually lower a burner or ignition source down the injection well. You start that, but while also injecting air or a mixture of air, maybe a higher percentage of oxygen, and that gives fuel to that fire, and you continue with that burner on until you've successfully ignited the formation. And then some of the oil will burn as you continue to inject air down hole. You will remove that burner, continue injecting air, and the fire front will advance as it moves towards the production well. And the interesting thing about this one is you get a lot of different mechanisms at work because you have water within the formation being vaporized into steam. You can also inject water vapor down with your air to get more steam drive, which helps cut the cost of injecting air because you're getting other mechanisms helping you produce the oil. But you also get the gas pushing out into the formation. You get a lot of different fronts, as you can see listed here, as you go from your injection well to your production well. And the really important thing with this is if you let that fire go out, you're pretty much completely out of luck, because if you're somewhere in the middle of this, if that's where your fire front is and it goes out, then you're not going to be able to relight that because your injection well is all the way over here. You're not going to be able to get it started again. So you're basically just out of luck for getting all that oil out of the reservoir. And I'll turn it over to Mohammed.
Thank you, Brett. Okay. Now I would be talking about the steam injection case studies. The 4 case studies we picked to talk about tonight: the Russian case study, the Canadian case study, the Chinese, and the American case study. We will go first with the Russian case study. The Russian increased efficiency by the time with the Russian, I didn't know that. The Russian increased efficiency with the time by the studies. They used foams, gels to maximize the efficiency. As a result, we have 33% decrease of water rate. We have 25% increase of oil rate. And also we have increase of the number of simulation cycles from 3 to 30 cycles. And now I will go with the Canadian. In the Canadian study, they improved the overall efficiency of the process. They also improved the contact between the well and the reservoir. They also used flow vents to control the flow of water. They used air injection. They used biodiesel. And also, as a result, we have 20% increase of the recovery. And we also have from 3 to 6% increase in the recovery factor. Then we will have the Chinese study. The Chinese use the kind of best methods of the steam injection. They used methods called multi-zone steam injection, and they used the use of chemical additives. And they also improved the process by using separated zone injection methods. As a result, for the Chinese study, we have from 7 to 8% increase in the recovery. We also have 40% increase of production and improvement. And last thing, we have 70% increase of the steam zone. And then last and not least, we have the American study. Here what I have for the American study. There's Trump. Number one, they used new techniques in cold lake field. Number two, they also used calculated reservoir heating. Number three, they fractured the formation by using high pressure injection. And then last thing, we have 30% increase of the air production. And then my partner will continue the rest. Thank you.
So I'm going to talk about some of the recovery mechanisms involved with this, and the first one I'm going to talk about is thermal expansion. Basically, thermal expansion is just when the volume of a substance is increased due to the temperature increase. As a result of obviously steam injection or any type of really thermal injection, both the rocks and the fluids within the rocks will be heated, therefore expanding, and that will actually cause a decrease in the pore volume. Obviously resulting in the oil being discharged into the fracture system. For matrix blocks that is heated to about 400 degrees 400 degrees Fahrenheit, thermal expansion accounts for nearly 20% of the original pore volume. The next one is capillary imbibition, and this is for water-wet reservoirs. And is actually when water in the fracture system will absorb into the matrix block through the smaller pores. This will cause the pressure internally to increase and will cause oil to exit through the larger pores. Some of the variables that can affect this are interfacial tension, wettability, and pore geometry. The next one, gas generation. Gas generation basically happens just when their chemical reactions happen due to the water-oil or water-matrix interactions. Some of the gases that can be released are carbon dioxide, H2S, and some of the light hydrocarbons. Even at certain temperatures, gas will even start to displace oil due to the fact that the water within the reservoir will heat up and turn into steam, resulting in oil being recovered similarly to that of a gas drive. Chemical alteration of oil. So basically, when you're using steam injection, the heat can change the molecular structure of the oils. It can also, which will then alter the chemical bonds. This will impact the density of the oil. For like a heavy oil, it is actually like if you heat it to around 570 degrees for the one experiment I was reading, it'll decrease the density by nearly 1%. And then the next one is alterations of rock matrix. This is basically as steam creates high temperatures, the structure of the pore filling materials may change. I mean, this is just evident with any temperature change, really. But the problem with it, in order to predict how it will really affect your oil recovery, you need to know the chemistry of both the rocks and the fluids. The next one is distillation, and this is basically when steam vapor passes past the oil. Some of the hydrocarbon components will evaporate into the steam. This will reduce the residual oil saturation, but due to the fact that vapor doesn't really pass through the matrix block itself, it mainly sticks to the fracture system, low amounts of hydrocarbons will actually end up being distilled out. And then the last one, cyclic pressure depletion, which we talked about a little bit earlier, is just the fact that when you're injecting into your well, you're going to have higher pressure, and then when you're producing, you're going to have lower pressure. This will just cause temporary pressure gradients that will result in the process accelerating for that time.
All right, so as you know, we should know by now, economics is one of the most important things that you need to consider when you're doing a project. So we wanted to give you a general overview of some things to consider when you're considering doing thermal injection. The first thing is going to be pretty general, like your price of oil. Obviously, that's going to determine if you do the project or not, especially with thermal injection, which tends to be in very oil-heavy areas. You also want to consider your reservoir type, if it's pretty extensive or if it's low API oil or high API oil. It's going to make a big difference. Then cost of operations. Well, specifically to this area, you're going to have lower drilling costs, so you want to consider if you have low drilling, completions, production costs. You know, you might be able to invest more in EOR, whereas if you're out in the Utica, your drilling and completions costs are really, really high. So it's something else to look at. Also, you're going to have to build a facility, usually, to make it economical in general. You're going to need one of these large, extensive facilities to really make it viable. So you're going to need a certain number of wells that you need to consider. You're going to need to know if you need 500 wells, 600, 10,000, and we'll see in the example I have in the next slide. And then something else to consider, if it becomes an option, you can do electricity generation like some of the other groups talked about. You could, if you have excess or if the wells die, you could produce electricity from these facilities if you want to make that commitment. So like I said, there's an example here with Chevron, they're a pretty good representation of the San Joaquin Valley because they own basically all of it, so their data is pretty reliable. So as I mentioned before, you're going to need facility costs, so your whole infrastructure of the facility itself, the pipelines you're going to need for injection, you're going to need a certain amount of wells, injection wells, so you're going to have to think about if you want to invest that heavily into something. But specifically for this area, they tend to not be produced regularly, like on I'm trying to think, just normal production methods. So you pretty much go straight from drilling completions to this EOR method of steam injection. So you don't have to worry necessarily about those production costs. So that's something to consider. But in this example, this is from 2009, so it's not exactly recent, but it's a pretty good representation. And I checked, they still have about 16,000 producing wells in this area, so that's still correct. And it's just to give you guys a better perspective on how much you can produce and how many wells it takes to produce, because obviously this is economic for Chevron to do, but it might not be economic for someone who's a much smaller company who can't make a commitment to building a facility or even getting in to use a facility like this. So there's a lot of things to think about for thermal injection if you want to go that route.